All right, and so here we have an example of a rational expression. And what I want to do is reduce it or decompose it into other smaller proper rational expressions that add up to this fraction, essentially. Okay, we're splitting it apart into smaller fractions that add up to this one. One expression that we're going to talk about is called an irreducible linear factor. Okay, irreducible linear factors. Basically, they're linear factors that you can't break down any further. Now, pretty much all linear factors are irreducible. So you may not even see the word irreducible mentioned. It may just be linear factors. Okay. In this case, we have what we call a reducible quadratic factor. Okay, so x squared plus 5x plus 6 is reducible because it can be factored into linear factors of x plus 2 and x plus 3. And so what we'll do is actually do that factoring. So this is x plus 7 over x plus 2 times x plus 3. Right? Now, once I have it in its factored form, I know that the original fractions that I must add in order to get to this, right, going the other direction, they would have to have an x plus 2 on the bottom and an x plus 3 on the bottom. I really don't need the parentheses there. So you'd have to have an x plus 2 and an x plus 3 because the LCD for these two factors, these two denominators, is their product. Okay? And so in order to decompose this into proper fractions, my numerators must be degree 0, right? If I have degree 1 on the bottom, in order to be proper, I have to have degree 0 on top, which are just constants. Now, I don't yet know what those constants are, so I'm going to just label them as A and B, all right? So what I need to do is try to figure out how to solve this equation for A and B so that I can get those corresponding constants, all right? And I'm going to leave this left-hand side off because that's just the unsimplified form. So I'm really just looking at the right two sides of this. So I want to solve for A and B. Now there's a couple different ways to do this. The one that I'm going to show you really utilizes the idea of a linear system or system of linear equations. The main idea is you start with this equation and we're going to multiply both sides by the least common denominator, okay? If I were to do that, I'm going to multiply the left-hand side, well, both sides, by the product of x plus 2, x plus 3. So I'm going to do that on the left. I'm going to do that on each term on the right. All right? So I'm just multiplying both sides of the equation by the same amount. It's this product. And it distributes to both terms on the right, so really every term gets multiplied by it. Okay? And what will happen then is that I can cancel common factors. So here I'd have an x plus 2 that cancels, an x plus 3 that cancels. Here my x plus 2's cancel, and here my x plus 3's cancel. And what I'm left with on the left side is simply the x plus 7. And on the right side I have a times x plus 3 plus b times x plus 2. Okay. Now this kind of looks like just a polynomial equation, but the a and the b are variables as well. So it's technically a 3-variable equation with a, b, and x. But if I expand this right side out, what you'll find is that you can match up terms. So I get ax plus 3a plus bx plus 2b. Now if I isolate my terms properly, you'll notice that the x term on the left side must match up to the sum of the x terms on the right side. In other words, 1x must equal ax plus bx. Well, what does that tell me about a and b? That tells me that a plus b has to equal 1. The coefficients must add up. All right, so I know then that a plus b has to equal 1. All right, so these original two coefficient or constants on top must equal 1 when added together. I also know that the 7 must add up or must equal 3a and 2b, right? So I know that 7 equals 3a plus 2b because the constant on the left, the constant of the polynomial, must add up or equal the constant of the other polynomial. Okay? If the two polynomials are the same, then the x terms have to be the same and the constants have to be the same. All right, and so this gives me a second equation. In fact, I'll write it in standard form. 3a plus 2b is equal to 7. Well, lo and behold, we have a system of equations here, right? With a and b involved. It's a two-variable system with two equations. And I can solve this using substitution or elimination. I'm going to go ahead and use elimination on this one, or addition, whatever, however you want to call that. And I'm going to multiply the top equation, not a fraction here. I'm going to multiply that by a -2 just to get rid of my b's. So this equation will become -2a minus 2b equals -2. So everything gets multiplied by a -2 on top. And the bottom I'm going to multiply by nothing. I'm just going to, or by 1. I'm going to leave it as 3a plus 2b equals 7. And then I'm going to add those equations together. The b's will drop out. The a's, let's see, -2a plus 3a is just a. -2 and 7 makes 5. So it tells me my a value is 5. And if I plug that a value back in, I know that a plus b must equal 1. So 5 plus b equals 1. If I subtract the 5, b must be -4. Okay? So that tells me then that if I were to replace a with 5 and b with -4, I'll get the two fractions that add up to the original. Now let's check and make sure that works. So basically my answer is going to be 5 over x plus 2 plus -4 over x plus 3. Now it's not really convenient to use plus and negative, so usually we'll just write that as a minus. Okay, but plus and negative is the same thing. So in theory, my original fraction breaks up into this one. Decomposes, I should say. Now let's just check and make sure that that works. I'm not going to expect you to check every one of these, but I'm going to do it just to show you how this actually works out. So as a check, I'm going to get a common denominator, which I know is the product of the two denominators, and I'm going to multiply on top. So this first fraction would become x plus 3 times 5 over x plus 3 times x plus 2. So I multiply top and bottom by x plus 3. And then the other fraction, a little space here, is going to be, I'm going to put the x plus 2 on top and bottom. So it's x plus 2 times 4 over x plus 2 times x plus 3. So I'm multiplying that on the top and the bottom. Okay. If I distribute here, I get 5x plus 15 over the product of x plus 3. Now I know the product of x plus 3 and x plus 2 is actually, I'm going to go ahead and write that out, x squared plus 5x plus 6. And over here, if I distribute the 4, I get 4x plus 8. Oops. And my denominator is also x squared plus 5x plus 6. Now I would distribute the minus, and that would give me 5x plus 15 minus 4x minus 8 all over this LCD, which I'll just write as LCD to keep it short. And when I combine these, 5x minus 4x, that's just x. 15 minus 8, that is 7. And my LCD is x squared plus 5x plus 6. So it checks out because that matches the original fraction that we started off with. Okay? So again, this is the process, this partial fraction decomposition is a process of starting with a relatively complicated rational expression and breaking it up into the sum of two simpler, or two or more simpler rational expressions. Okay, so this is technically the answer right here. The rest of this green stuff here is just my check to make sure it worked. Again, I'm not going to always require you to check, but I think it's good practice at least to do that occasionally to make sure you've got the right process down. But mine is just to really show you that it works, to verify it. The other thing I want to mention too, before I cut this video, I was going to cut this, is that when you have a quadratic, or when you factor down into irreducible linear factors, in fact, even more than just irreducible, I really should call this non-repeated. I mean, they are irreducible. That's redundant though. Irreducible linear, all linear factors are going to be irreducible. But these are actually non-repeated, which means the powers are all 1. That's really what I should have had on there anyway. Non-repeated linear factors, the non-repeated linear factors always break down into, you separate them off, and then you put a constant over top. And again, the reason for that is because you always want the numerator to have smaller degree than the denominator.